Okay guys, so we are going to start this discussion on recovery, recrystallization and grain growth, which is very important from gate point of view. And if you want to understand heat treatment, then also you need to understand this heat treatment process. Give me a minute. Is it audible to all of you? Thank you. Am I visible? Okay. Just give me some more time. Okay. So, suppose you cold work upon some material and suppose you are rolling something, huh? You have this one roll and then there is the another roll. Let me check shapes. Sorry. We have one roll over here and then there is another roll there. Now we are feeding a plate in between these two rolls. Okay, Suppose this is a plate. So as the rolls will rotate, it will squeeze the plate in between. So these were the grains which were initially there inside the plates. These are the grains that I am showing you. So what happens as you roll it down in the rolling direction, these grains will elongate, isn't it? And if you see over here, you will find these elongated grains, right? So these grains over here that I am showing you, these are the unstrained grains, while these grains over here are strained grains. And remember, you are doing cold working. So what happened? As you do this rolling and as it is the cold working process, so what happened? These grains will elongate. As the cold working is happening, so strain hardening will happen, right? Strain hardening is happening means what? Already dislocations were there in the unstrained grain, but now due to cold work, what will happen? The dislocation density will increase, right? As already you know, dislocations generally form during solidification, and further multiplication of dislocations occur during cold work. So as you did this cold work, grains were strained, dislocations piled up near the grain boundary, it created back stress. Due to that, strain hardening happened. Moreover, dislocation density increased. Not only that, you see here the grain, it is unstrained, and here the grain has been elongated. So this elongated grain will have more surface area as compared to this unstrained grain. So as the surface area increased, that means what? Total grain boundary surface area increased, right? This is the grain, this is the boundary. As it will elongate, total grain boundary surface area will increase. Grain boundary surface area increases, dislocation density increases. So means you can say, or you can anticipate, that by doing the cold work, grains strain, or you get the strained grains. That means what? Dislocation density increases, or total grain boundary surface area increases. Or you can anticipate that by during the cold work, you store some energy, you store some internal energy in the grains in form of increased dislocation density and increased grain boundary surface area. By straining the grains, what you did, you stored some internal energy, in terms of what? Increased dislocation density, increased total grain boundary surface area. So you can further conclude from here कि as dislocation density is increasing, grain boundary surface area is increasing, movement of dislocation will now be more resistant. That means what? Strength will increase while the ductility will decrease, right? So due to cold work, strain hardening appears, during which dislocation density increases, grain boundary surface area increases, strength increases, and at the same time ductility decreases. Now my dear, if you take the strained grain and you add heat into that strained material, right? So what happens? Just a minute, hold on. Hello. हाँ हेलो. हाँ. अच्छा क्लास में 7 बजे बात करते हैं. Hello. हाँ now. I'm sorry, it was my father's call. Okay. So strength increases and ductility decreases. Now what I was saying, when you add the heat into the strained grain. So let me go to the next slide. Let's take the strained grain now. I'm sorry. Let us take the strained grain now. This is the strained grain over here. Now let us add heat into it. So as you add up the heat into it, so it will at first undergo a stage of recovery. As you add up the heat, my dear, what will happen? Suppose this is the grain boundary. This side atoms are there. And then as you can see, dislocation is also here, over here, right? Dislocation. Atoms are missing from here, so dislocations, right? Now this side of grain, another atoms are there. So as you add the heat, the temperature will increase, and at increased temperature, atoms diffusion will start and it will enhance. So what will happen? These atoms will start to diffuse to this region. As the atoms diffuse to the dislocation site, the dislocation density will decrease, which were piled up near the grain boundary, right? As the dislocation density decreases, then the back stress that was being created by those dislocation densities which were piled up near the grain boundary, that will decrease. So back stress will decrease. So there will be a decrease in the strength of material, right? A slight decrease will be found in the strength of material during this stage, and there will be a slight improvement into the ductility of material, because dislocation density will decrease a little. So strength will reduce a little while ductility will increase a little during the stage of recovery. I'm not saying that all the cold work stresses will be relieved during this period. No, my dear, all the cold work stresses will not be relieved during this period. Instead, some of the cold work stresses will be relieved, so strength will reduce a little, ductility will improve a little. All the electrical properties and thermal properties will be rolled back to the pre-cold worked state. All the thermal properties and electrical properties will roll back to the pre-cold worked state during the stage of this something called as recovery. Now my dear, after recovery, what will happen is something called as recrystallization into the grain. Recrystallization into the grain. Now, what is this recrystallization? It is said that recrystallization means grains become equiaxed and strain free. This is what happens during recrystallization. Grains become equiaxed and strain free. Now my dear, you will be thinking, what is this equiaxed and what is this strain free, right? So actually this equiaxed means almost same appearance from all sides, and this strain free means no strain into the grain, no cold work stresses into the grain. That is what we call as strain free. So this is what will happen during recrystallization. All of the grains will become equiaxed and all of the grains will become strain free. So how does it happen? Let me show you. You see, as you cold work the material, so this was the strained grain after recovery. In that strained grain, there might be some smaller grain and then there will be some larger grain. So what will happen? From a smaller grain, atoms will start to diffuse towards the larger grain. Suppose this one is a smaller grain, this one is a larger grain. If the atoms diffuse from like here to this grain, what will happen? You see, in this side orientation is different, in this side grain orientation is different. But as these atoms will diffuse to the another grain, so what will happen? The grain boundary which was here, and what is grain boundary? The region of orientation mismatch, right? So here different orientation, here different orientation, here different orientation. Now as these atoms will diffuse to this grain, what will happen? This grain boundary will shift towards this side. So this smaller grain will become further smaller, this larger grain will become further larger, and will keep happening if you keep adding the heat. So a time will come when like this grain will no more be there, in place of that you will find only one grain like this, as I'm showing you there. Like this, there will be this only one grain. So this grain boundary will also after some time will not be there, because all these atoms from there will diffuse to that grain. So now what will happen? This grain is gone, this grain boundary is gone, and you have only this grain over here, right? Only this grain over here. So you see, now this grain is like looking like its appearance from all side is looking like almost same. So now we will say it became equiaxed, and at the same temperature as you added the heat, what will happen? All the dislocations will go back to their newer positions, and the dislocation density will decrease furthermore due to enhanced atomic diffusion. So grains will now not be having any kind of cold work stresses. So during this stage, what will happen? Strength will further reduce and ductility will further improve. Now, the temperature at which this happens the temperature at which this happens is what we call as recrystallization temperature. Now, generally, the recrystallization temperature is defined as the temperature at which all the grains, recrystallization temperature is defined as the temperature at which all the grains become equiaxed and strain free. Recrystallization temperature is defined as the temperature at which all the grains become equiaxed and strain free. And my dear friends, this recrystallization temperature for most of the metals, this recrystallization temperature for most of the metals and their alloys range between 0.3 of the melting temperature to 0.5 of the melting temperature. For most of the metals and their alloys, it ranges between 0.3 of the melting temperature to 0.5 of the melting temperature. Okay. My dear friends, it is also believed that recrystallization temperature for alloys is more than pure metal. Recrystallization temperature for the alloy is found to be more than pure metal. And yes, it is true. For example, if you see recrystallization temperature of iron, that is pure iron, is about 400 degrees centigrade, while recrystallization temperature for steel is about 1000 degrees centigrade. You see, steel is the alloy of iron, that is pure metal. Now, why does it happen? My dear, as I told you in the previous slide, during recrystallization, atoms will diffuse from this one grain towards this another grain. What happens in case of pure metal? There is no impurity, only iron atoms are there. But in case of steel, along with iron, there can be another impurity atoms. Mostly carbon will be there, and many things further, many other impurities, other solutes can be there. What happens? As the atoms from the one grain wants to diffuse towards the another grain, then as you heat the metal, as you heat the steel, the solutes like carbon atoms or some other atom, if suppose some molybdenum is there, chromium is there, tungsten is there, so these impurity atoms pile up near the grain boundary. They pile up near the grain boundary. As they pile up near the grain boundary, they resist the diffusion mechanism. They resist the diffusion mechanism of the atoms from one grain towards another grain. They impede their movement. They impede the diffusion. And if it does not happen, you see, recrystallization will not happen so easily. Right? Rate of recrystallization will further decrease. So recrystallization temperature will increase. Did you understand that? In case of alloys, it is believed that impurity atoms segregate near the grain boundary, right? And hence they resist the movement of atoms, and hence the recrystallization temperature for alloys is more as compared to pure metals. समझ में आ गया? All of you understood? Now my dear, one more thing is here. Recrystallization temperature is found to be inversely proportional to degree of cold work. Recrystallization temperature is found to be inversely proportional to degree of cold work. The reason for that is, let me show you through an example. Suppose this is A, 50% reduction was done, it became like this. B, same specimen, same size, same material, everything is same for B, but the reduction is like only minus 20%. B is this. Now, here you can say that relatively you did more cold work, or you can say degree of cold work is more. Here you can say degree of cold work is less, right? In case of A and B, both are of same material, both size is same load was applied, every process parameter is same, but reduction that we did in case of A was more, reduction that we did in case of B was less. So in case of B, less cold work was done, less degree of cold work. In case of A, more degree of cold work. Now, if you add heat in B and you add heat in A, then what you will find, ki A will recrystallize. Recrystallization temperature of A, you will find it is less than the recrystallization temperature of B. That's what you will find. That is what, in short form, recrystallization temperature is inversely proportional to degree of cold work. My dear, but now the question arises. As I told you, recrystallization temperature is inversely proportional to degree of cold work. Now the question arises that why does it happen? Why like more cold work then the recrystallization temperature is less cold work then recrystallization temperature is more? Let me give you an analogy for that, or let me give you an example for that. Suppose you have a balloon. And this is like daddy and this is the sun. Okay. Now in one case, take high speed camera, record this whole situation, right? Take a balloon. Now make the daddy sit over the balloon. No doubt into that the balloon is going to elongate. Now the balloon will become something like this, elongated. Now daddy was sitting here. Now daddy comes down. He is no more sitting. So what will happen? This elongated balloon will pop back to its original shape. There will be a time taken in this. Let us say that time taken in popping back is T daddy. Second case, on the same balloon, let the sun sit now. As the sun sits on the same balloon and then he comes down, again there will be some time taken, right? In the time in which the balloon pops back. In which case the balloon will pop back faster. when daddy comes down or when son comes down? No doubt into that. When daddy comes down, then in popping back of the elongated balloon, the time taken will be less as compared to when the sons come down from the balloon. You know why? Because the driving force which is making the balloon to pop back to its original shape, is what? The driving force for this to make it pop back to its original shape is the difference in stored internal energies of elongated and original balloon. As daddy sits on the balloon inflates, it elongates. That means what? More internal energy was stored. As son sits there on the balloon, his mass is less. So less internal energy was stored into the balloon. Right? Now, in which case the difference in internal energy will be more? When the sun is sitting, the difference in internal energy will be less. When daddy is sitting, the difference in internal energies will be more. So in case of daddy, the driving force will be more, which will make the balloon pop back to its original shape, isn't it? Time taken will be less. Means rate of popping back will be more in case of daddy, so balloon will inflate sooner. The same analogy will fit into this case also. You see, my dear, what happened? Here in this case, more amount of cold work was done. Here in this case, less amount of cold work was done. Right? Here less cold work was done. So what will happen? As you start adding the heat, for recrystallization to happen, the responsible driving force is the difference between strained grains, difference between internal energies, difference between internal energies of strained and unstrained grains. The driving force responsible for the recrystallization to occur is the difference between the stored internal energies of strained grains and unstrained grains. So my dear, in case A, you are doing more amount of cold work. So difference in internal energy of the strained and unstrained grain will be more. Right? While in case of B, the difference in internal energies will be less. As this happens, so as you add up the heat, in case of A, the rate of recrystallization will be more, so recrystallization temperature will be less. In case of B, the difference in internal energy is lesser as compared to A. So rate of recrystallization will be lesser, so recrystallization temperature will be more. Is it very much clear to all of you? I hope it will be clear. So my dear friends, during recrystallization, as I told you, the grains will become equiaxed and strain free like this. It will become equiaxed and strain free, something like this. Then my dear, what happens? As you leave this recrystallized grain at the same elevated temperature, as you leave this recrystallized grain at the same increased temperature, then the next thing that will happen there is what we call as grain growth. During the grain growth process, you will find the grains will enlarge like this. How does the grains enlarge? It is said that, and it is true, that the grain size increases, or you can say the larger grains become further larger. The larger grains become further larger on the expense of smaller grains. Are you getting me? I'll show you through this. Don't worry. Suppose this is the grain boundary. In this is the one grain, and the orientation of atoms you can see as I am drawing these atoms. I'm sorry here. In this grain, the orientation of atoms is like this. While in this grain, another grain is there. The orientation of atom is a bit different. You can also see left side that the grain is there. It is larger in size as compared to the grain which is on the right hand side that I am just drawing. Now at elevated temperature, what will happen? This atom will diffuse towards this side. From smaller grains, the atoms will diffuse towards the larger grains, as I have discussed earlier. Why will it happen? On the plus platform, I will be discussing that. Unacademy plus platform, right? So as the atoms diffuse to the left hand side, right, what will happen? The region of orientation mismatch was initially here. Now these atoms which diffuse to this side, their orientation of these atoms will become like this, right? Their orientation will change. So region of orientation mismatch, that is, this is the grain boundary. This grain boundary will shift towards right. So now the grain boundary will be like somewhere here. This will be the region of orientation mismatch. Now the grain boundary shifted. And you know, the movement of grain boundary will be in opposite direction of the atomic diffusion. That is very much clear. This will keep happening, and a time will come this whole smaller grains atoms will diffuse towards the larger grain. This will become one single grain. All the atoms will have now same orientation in the two grains. This is how the grains grow. This is how the grains grow. So as the grain growth appeared, you see, as the grain growth has happened over here, you see, in this case and in this case, right? Two cases are there, in which case the number of grain boundary is less, or actually telling you in which case the total grain boundary surface area is less. You see here in this case total grain boundary surface area is like 1 unit plus 1 2 unit plus 1 3 unit plus 1 4 unit plus 1 5 unit plus 1 6 unit grain boundary surface area. Here how much? 1 unit, 2 unit, like something. No doubt that this will be relatively less as the grain size will grow, the total grain boundary surface area will decrease. And my dear, this is the grain boundary which impedes means resists the movement of dislocation. And you all know the movement of dislocation is responsible for plastic deformation. If the movement of dislocation is easier, plastic deformation is easier, strength is less. As movement of dislocation is difficult, plastic deformation is difficult, so strength will be more. During grain growth, grains enlarged in size. Larger grain become further larger. Larger grain became further larger on the expense of a smaller grain. Due to that, total grain boundary surface area decreased. As the total grain boundary surface area decreased, my dear, so relatively now the movement of dislocation will have lesser resistance. So strength will further decrease and ductility will further increase. That is what will happen during this something called as grain growth. If you look from here up to this, then what you will find is this grain size increases. This grain size you will find that grain size will increase. Here I am showing you the grain size, right? So what are the points to ponder? The points to ponder now after this discussion is, I'm sorry dear, during recovery, what happens? Stress decreases a little, ductility increases a little, then one more point, all the, or you can say cold work stresses are not relieved fully. There will be still cold work stresses. Some properties like electrical and thermal properties will roll back to their original state, right? Now my dear, what will happen during recrystallization? Generally, as you know, recrystallization temperature varies between 0.3 of melting temperature to 0.5 of melting temperature, right? Then these are very very important for gate. These are very very important points for gate. Then my dear, recrystallization temperature of alloy will be more than recrystallization temperature of pure metal. Then my dear, recrystallization temperature will be inversely proportional to degree of cold work. I explained the reason for that. Then my dear, you know, for recrystallization to occur, at least 2% to 20% of cold work is required. Here, yes, you should remember these two words. Grains become equiaxed and strain free. Yes, what the last point I said you, if for recrystallization to occur, at least 2% to 20% of cold work is must. Why is it so? You see, if someone gets a bacterial infection, he gets a bacterial fever, right? Then if you give the medicine, then his health will improve. Are you getting me? If someone gets a fever, you give him paracetamol, then his fever will go down. If he is not having any fever, if you give paracetamol, do you think his fever will go down? Same way, if recrystallization has to happen, during recrystallization what happens? All the cold work stresses are relieved. That's why the grains become equiaxed and strain free. If cold work has not been done, there is no cold work stresses. So even though if you heat up, what will happen? No cold work stresses is there, so nothing will be relieved, so no recrystallization will happen. And that is why, my dear, it is said that grain growth needs not to be preceded by recovery and recrystallization. That means, even though if recovery and recrystallization does not happen, because they will happen only when cold work is done. If you do not do any cold work, no recovery, no cold work, then no recovery, no recrystallization, then what will happen? Directly grain growth will happen. Directly grain growth will happen. Is it very much clear to all of you? Cold work for recrystallization to happen, at least this much, 2% to 20% of the cold work is required. Now, how much cold work is required? That will depend on the type of material. For example, steel gets strain hardened very easily, but strain hardening is not that easier for aluminium. So no doubt, aluminium's recrystallization rate will be less if you cold work upon it, right? You will have to do more amount of cold work to induce cold work stresses into it. On a steel, even if you do lesser amount of cold work stresses will induce into it. Is it very much clear? So, my dear, this is what happens during recovery, recrystallization and grain growth. During recovery, recrystallization and grain growth. So, my dear, this is the basic of heat treatment. You study the heat treatment of steel for GATE and IS exam. So, this recovery, recrystallization and grain growth, if you understand, then it will be easier for you to understand heat treatment. And this topic is very, very important for all the state exams, that recovery, recrystallization, grain growth, for all the competitive exams in engineering field. Every year you will find this question appearing into some exam: recovery, recrystallization and grain growth. So this is what the point to ponder that I gave you. You must remember. This will be very much helpful for all of you in the exam. And this very, very important for GATE: recrystallization temperature inversely proportional to degree of cold work. Along with this, recrystallization temperature of alloy is greater than recrystallization temperature of pure metal. So you remember it, and you also understand that I discussed now, right? This video will be available on YouTube. So repeat that class watch that in the offline mode. This is a live class, right? And yes, we are launching on Unacademy platform, let me tell you, two courses now. One course from 18th, that is tomorrow, 6 p.m. to 8 p.m. daily, 12 days class. In this 12 days class, I will be discussing every single question of manufacturing engineering which was asked for past 30 years in GATE. So those who are still unconfident, not confident in this production paper for GATE, which is very very important as they ask for 15 marks, they must join this, right? They must join this course. This is a 12 days course. It will take around 24 hours. I will be discussing every single question which were asked for past 30 years in production, right? So tomorrow evening means 6 p.m. I am starting this course. It will run for 12 days. It will be like around 24 hours, and you can take a subscription on Unacademy for 1 month. You can use this code RK007 for 10% discount. And if you want further any kind of help from me, you can call me 76759 This is my number. You can send me WhatsApp or you can even directly call me, right? So let's meet in the next session, that is the special class session on Academy Plus platform, that is at 11 o'clock, right? 11 p.m. tonight. Okay, till that, all of you, bye bye. See you in the next session on YouTube. Okay, thank you, thanks a lot.